Okay, so let's look at some proficiencies of some enzymes, and in particular, this is a figure from an old science paper. I think you can find the citation in the notes panel to this PowerPoint presentation. I'll post this PowerPoint presentation along with this video. Okay, and what do we see here? Well, what's graphed here basically is the catalytic proficiency of a number of different enzymes, including Omp decarboxylase, which we're just going to abbreviate ODC, Omp decarboxylase, and then a number of other representative enzymes, staphylococcal nuclease, STN, adenosine deaminase, carbonic anhydrase. You can just look here in the figure legend to see what all these various abbreviations stand for. Okay, and so for each enzyme, what have we done? We've plotted 2 points. Okay, the upper point here then is the catalytic efficiency. It's the Kcat over Km for that enzyme. And the lower point here is the Knon for that enzyme. Okay, and so since catalytic proficiency is the ratio of Kcat over Km divided by Knon, the longer this line here, the greater the catalytic proficiency of the enzyme. And so what you can see is that compared to all the other enzymes in this graph, Omp decarboxylase, ODC, has the greatest catalytic proficiency. And in fact, it's one of the most proficient enzymes that have ever been discovered. There's maybe 1 or 2 other enzymes that are as proficient or maybe slightly more proficient. It turns out that those are all decarboxylases as well. And the reason that decarboxylases have to be such proficient enzymes is because decarboxylation reactions are inherently difficult reactions. They have they're reactions that in the absence of a catalyst occur at an extremely slow rate, right? And so the Knon for Omp decarboxylase is something like 10 to the minus 16th per second. And so that would mean that the half-time of this reaction is something like, I think it turns out to be 78 million years. Okay, so if you took a sample of Omp and just allowed it to spontaneously decarboxylate, you'd have to wait 78 million years for half of it to decarboxylate, right? All right. So really, at core, then the reason that ODC is such a proficient enzyme is because it has such a difficult reaction to deal with. If we look here up at the other end of the graph, we see that a lot of these enzymes have very similar Kcats over Km, right? And so actually these 2 dashed red lines here then represent the zone of catalytic perfection. They represent 10 to the 8th to 10 to the 9th molar per molar per second. And so we can see a lot of enzymes have achieved, catalytic perfection. They're in that range. ODC, it turns out, is just below that range. So ODC is pretty close to catalytic perfection, but perhaps it's not quite there. So in terms of catalytic efficiency, you could say that ODC is not as good as carbonic anhydrase or triose phosphate isomerase. But in terms of catalytic proficiency, which many would consider the ultimate measure of enzyme quality, it is significantly better than those enzymes. Okay, so just to summarize then, catalytic proficiency, which is Kcat over Km divided by Knon, in other words, the catalytic efficiency divided by Knon, may be a better measure of enzyme quality than catalytic efficiency, as there's no theoretical limit. And in addition, it approximates the binding constant for the transition state enzyme complex, and in that way can be thought of as the ultimate measure of enzyme quality. So what is the catalytic proficiency for ODC? Well, it has a catalytic efficiency of about 10 to the 8th per molar per second. And as we saw, it has a catalytic it has a K-non of something like 10 to the minus 15th, so 10 to the 8th divided by 10 to the minus 15th is approximately 10 to the 23rd per molar. So ODC then appears to bind its transition state with a binding constant of something like 10 to the 23rd molar to the minus 1. That's a tremendous binding constant. Okay, so let's think about what that means. So here is the Omp decarboxylase reaction. Here's OMP. We just are abbreviating the ribose 5-phosphate portion as R5P. And so here then is the uracil ring with this extra carboxylate group attached to the 6 carbon. And in the decarboxylation reaction, we think what happens is that these electrons move in here, and these electrons then move out here onto the C6 carbon atom. And so in the transition state, we're forming this double bond while we're breaking this bond between this carbon atom and this carbon atom. Okay, and so this is the transition state. And then finally, we completely break this bond. We release then CO2. Okay, and the other product then of this first step is just this UMP anion, where we have a negative charge on the uracil ring. And then to complete then the transformation, we need to protonate this carbon atom to generate UMP. So this is the transition state, and presumably, although we'll see that this might not be completely true, presumably then ODC binds this transition state with a binding constant of something in the range of 10 to the 23rd molar to the minus 1. So how can ODC bind this transition state with such a tremendous binding constant? Well, normally binding constants in this range are only observed for covalent bonds. Many enzymes, and I'm sure you learned about some of them in 153A, do make covalent complexes with their transition states. However, ODC, as far as we know, is not one of them. It does not form a covalent complex with its substrates. So what's going on?